I'll start off, actually I'll give a little background on myself. So I've been in the feed industry for 33 years now. I've been with Balchem the last 10 and a half years. I've had 3 different roles there. I started off doing technical support, mainly for the Eastern US and Canada. And then I spent 3 years managing globally what we call our protein platform. And those are our Rumen protected amino acids, our AminoSure products, and NitroSure, our encapsulated urea. And then the last 4 years, I've been the director of technical support for Animal Nutrition and Health Group. I also have the pleasure of overseeing all of our external animal research that we do. So a lot of what Dr. Santos showed today, I've been very involved with that from an internal perspective. So Samuel already gave the background there on Balchem. But as far as encapsulation technology, I always say Balchem's sort of known for 2 things. We're the world's largest manufacturer of choline chloride. And choline and businesses related to choline filter throughout all of the businesses in Balchem. But we're also basic in microencapsulation technology. So the company's been around since 1967. And we've been encapsulating products since 1967. We actually started out in this business. It's a core business of Balchem as far as encapsulation. So the largest part of Balchem's business is actually a human nutrition and health business. The animal business is the second largest part. So about 60% of our business globally is this human nutrition and health business, and 30% is our animal nutrition and health business. So there are a lot of applications for encapsulates actually in our human businesses. Encapsulates related to baking. We make encapsulates related to confections. So, I don't know, gummy worms, are you familiar with gummy worms? So we make an encapsulate that gives it that flavor, actually. That's an encapsulate that we make. We make encapsulates that go into meat products that help preserve shelf life of the meats. So there are a lot of applications, actually more than there are in the animal business. We have hundreds of encapsulates that we make for our human businesses, actually. As far as our animal business, so there are a lot of applications of encapsulates here as well. So in the monogastric species, we encapsulate tannins for monogastrics. We encapsulate acids. We started a pet business about 7 years ago. So we encapsulate acids for pH control in pet foods and structure and forming technologies to help make pet treats and other things related to the pet business. As far as ruminant applications, certainly ReaShure XC, which we've talked about. ReaShure brand has been around for 25 years now. We introduced ReaShure in 1999. That was actually our first foray into the animal business. We were in the human and chemical business prior to that, but ReaShure was the first time that Balchem actually got into the animal business with the ReaShure product. Encapsulated niacin, NiaShure, Rumen protected methionine, AminoShure XM, Rumen protected lysine, AminoShure L, and NitroShure is our slow release urea product. So encapsulation technology, there was an article, this appeared in Feedstuffs magazine back in 2011. And the author of this actually said not all encapsulated products are created equally. Consequently, there are vast differences in their efficacy and stability. And that's definitely true. And I'm going to show you a lot of examples of this during the presentation. So encapsulation is a very generic term. There can be very large differences between products that protect the same compound. What's that variation due to? So some of it's the starting form of the product, how it's included in the product. Certainly the coatings can vary as far as amount and composition and so forth, and the actual manufacturing processes can differ. So microencapsulation, it's a core technology of Balchem, as I explained earlier. And basically what we're doing is we are, in the animal business, of course, we're taking a nutrient and we are totally encapsulating it, in our case with lipid technologies. So this is a micrograph of one of our encapsulates. So you can see the lipid coating here. This is the active compound in the middle. So our animal encapsulates they're totally encapsulated. They're what we call true encapsulates. So encapsulates differ in design. So the basic design can be very different. The technology of encapsulation can vary. And then performance can certainly vary. So stability and feed mixing and TMR stability can vary, as well as animal performance. Again, differences in encapsulation are due to starting form and inclusion rate of the nutrients. So if you take methionine, for instance, Rumen protected methionine. There are some products that are as low as like 33% methionine, and some are 85% methionine. So the inclusion rate of the active nutrient can vary. The coating systems utilized can differ. These technologies differ. Certainly the composition of the coatings can vary drastically, as well as the manufacturing process. So there are a lot of different ways to encapsulate products. These are some of the different technologies that are out there that are used in different industries. A lot of these are used in the pharmaceutical industry. There can be single coating encapsulates, multiple coating encapsulates. You may encapsulate a product with irregular shape. There's this matrix encapsulation. There may be encapsulates with multiple actives. And there's a technology called plated liquid. And these will all have very different characteristics. And you can see here that animal encapsulates come in all shapes and sizes. These are not all Balchem products here, but you can see how much these products vary in shape and size. So there are a lot of different ways to encapsulate nutrients, but in the agricultural industries in general, there are two basic types of encapsulation. The first type is what we refer to as matrix encapsulation or spray-cooled encapsulation. That would be the example here on the left. So the analogy that we use there is chocolate chip cookie dough. So if we were encapsulating methionine in this case with a matrix encapsulation, we would be taking lipids and mixing them with D-L-methionine and creating particles of that product. So in general, if you think about this analogy where you're making a matrix, there's always some of the active compound at the surface of the product. So in general, a matrix encapsulation is a little less expensive way to encapsulate, but they tend to have reduced protection and reduced stability. So ruminal stability tends to be less with a matrix end cap. The analogy on the right is true encapsulation. All of the Balchem ruminant products that we make are true end caps. You may also hear these referred to as single layer coatings or multi-layer coatings. The analogy we use here would be an M&M. So basically, we're creating a core that contains the active compound, and we are completely enveloping it in layers of lipid in our case. So with a true end cap, there's no compound at the surface, and they tend to have higher levels of protection and ruminal stability.
Would they be more expensive to make?
Slightly.
Slightly.
Slightly. It's not a huge difference. Yeah, slightly. So I love this picture. This was taken actually before I started with the company. This is an old picture here, but this is a true encapsulate on the top. These are lysine products actually. True encapsulate, matrix encapsulate, and this is just a simple water test. These are these two products put into room temperature water. So the flask on the left has the true encapsulate. The flask on the right is a matrix lysine end cap. So of course, the lysine used in both these products is lysine hydrochloride. So at time zero, so immediately when they're put into water, you can see the two products look a little different. This is 30 minutes. This is after 30 minutes in water. And you can see, start to see a big difference between the two products. The product on the right, the water's starting to change color. That's lysine hydrochloride being liberated into the water. This is a picture after 2 hours. You see a major difference here, and this is after 4 hours. So that matrix end cap in this case is not stable even in water. You can imagine the ruminal environment's even harsher than this, right? You've got constant feed churning and mixing in the rumen as well as a lot of feed particles in there, and a higher temperature than room temperature. The other thing that all of our products have are freeze-thaw stability. So some of this goes back to all of our baking applications that we have for our end caps. So a lot of our products, they go through freeze-thaw cycles as they're being used for food applications. So we make sure that all of our end caps can withstand freeze-thaw cycles. Both of these products on this slide are not freeze-thaw stable. So the pictures on the top are before freezing. Picture on the bottom is after freezing. So you can see after these products freeze, you can see these cracks or fissures that are forming in those compounds. We occasionally test products that are not freeze-thaw stable. There are some products out there that are not freeze-thaw stable. As you can imagine with a ruminant end cap, if they're not freeze-thaw stable and they go through a freeze-thaw cycle, you're going to lose ruminal stability of the product. So this is just a test here. So the product on the left is freeze-thaw stable. I'm sure this is a reissue. I can just tell by looking at the numbers here. So before freezing, it's 90% rumen stable. After freezing, still 90%. This will be a competitive product. This product was about 80% rumen stable prior to freezing. After freezing, it lost basically half of its ruminal stability. It's only 40% rumen stable after a freeze-thaw cycle. So we we do a lot of testing, and we occasionally run into products that aren't freeze-thaw stable. That will really affect the efficacy of the compound. This is an example here. So this is NitroSure on the left, so our encapsulated urea product. This is under a microscope and with a dye added to it. So this is after a freeze-thaw cycle. So the NitroSure does not absorb any of the dye. That means it's still intact. There are no cracks in the product, basically. This is a competitive encapsulated urea product on the right. When there's dye added to it, you can see the fissures here in that product. That product's not freeze-thaw stable. So it's going to have very poor ruminal stability in that case. So why do we encapsulate nutrients for ruminants? And Jose talked about this with choline. So some of the work done by Rich Erdman in the late 1980s. So if we were to feed choline chloride to a dairy cow, 98 to 99% of it's going to be degraded in the rumen. The rumen microbes love choline. So niacin's about 95% degraded, and most of the amino acids are very highly degraded in the rumen as well. So we need to encapsulate them to get them through the rumen intact. So what are some good characteristics of a good rumen-protected product? So the first feature we look at, so whether we're designing brand new rumen encapsulates or we're improving existing ones, this is sort of the thought process that we go through. NitroSure is an exception to this. NitroSure is encapsulated urea. We actually want that to break down in the rumen just gradually over time. But amino acids, choline, et cetera, for a dairy cow, we want them to bypass the rumen. So first thing we look at is good ruminal stability. We want most of that product to get through the rumen intact. I always say if you have poor ruminal stability, you sort of lose the game right from the start if you don't have good ruminal stability. So we want good ruminal stability. We want as much intestinal release as possible, right? We want that animal to be able to absorb as much of that nutrient as possible. So when we're developing new products, we want products with good ruminal stability, good intestinal release. The third step, once we get that, is we look at feed and mixing stability. There's honestly not a lot of research that's published on this out in the literature, but we look at this in the product development process. We do not want to put a product out in the market that doesn't have good feed and mix stability. And I'll show you some examples of that. So we go through the first two steps, develop lots of prototypes, in some cases hundreds of prototypes, developing a new product. Once we identify good prototypes, we put them through feed and mixing stability testing that I'll show you. If they pass that, then ultimately we do the research to prove biological response. We want to make sure these products actually work for you and your customers. If an encapsulate's compromised in any of these three functions, it's not going to work as delivered. So I said if you have poor ruminal stability, you lose right out of the gate. Actually, if you fail here, you've already lost. That's before the cow even eats it. So that's probably actually the most important step right there, feed and mix stability. The product's got to hold up. Think of everything that these end caps go through in the feed mill, being transported to the farm, being mixed in a TMR. There's a lot that these products go through before the cow even eats it. So there's a lot of testing, a lot of types of testing that can be done to evaluate encapsulated products. Certainly there are in vitro techniques, in situ techniques, and ultimately in vivo techniques in the animal. So let's talk about ruminal stability first. So in vitro techniques, they're very important when it comes to developing new products. We can't immediately go to animal trials as we're developing new products. So these in vitro methodologies are really important. I think they're quite important as a ranking tool when we're developing new products and trying to pick new prototypes to put into the animal. In vitro testing is not the end all and be all though. Ultimately, it's the in vivo results that matter in the animal. But these are different rumor protected lysine products. So this is using an in vitro, it's called the MSPE method. This was developed in Mike Van Amber's lab at Cornell University. And these are just some different rumor protected lysine products that were put through this in vitro testing, looking at the ruminal degradability step. And you can see some differences here. They all look pretty good in vitro. These products are anywhere from 13% rumen degraded up to 29% in this case. So these are some competitive products. This is AminoSure L. This is a new product that we're developing on the right. This is in situ release. So this is actually putting it in the rumen of the cow, measuring in situ release. At this case, 0, 6, and 12 hours. And you can see there's some pretty big differences here in situ, very different from those in vitro results. So these are some different products here. This is looking at percent release in situ. So these higher releases not good, right? We don't want a lot of release in situ. So here's a product that's over 90% released in situ at 6 hours. Huge variability here. Not showing up in the in vitro test, but in situ we see large differences here. So we've got two products down here that are less than 20% release in situ versus some of these that are well over 50% release, almost complete release in some cases. This is rumor protected choline products, so a lot of different products here, and you can see are huge differences here in the products. So this is in vitro testing again, using that same technique from Cornell University. You can see some of these products, they're 100% released in vitro. They're not rumor protected. And we run into that with some of these choline products that are on the market. A lot of these have very high releases. Here's ReaShure XC right there with the lowest ruminal degradability. These are in situ values here again. So this is looking at percent remaining in this case. So in this case, the numbers at the top of the graph are better. So there's ReaShure XC and ReaShure with good in vitro stability. Here are some products that at 8 hours have over 50% release. There's some products that are over 80% released in situ. Here's a product, not sure why it's encapsulated, it's not working. By 8 hours, it's all gone in situ. Lots of differences between products here, just in this ruminal stability phase. Intestinal release, bioavailability. So in vitro techniques, we'll start with that. again, the MSPE. So what we're paying attention to here actually is this gray bar. So the gray bar would be the estimate in vitro of bioavailability, essentially. So this dark blue bar, that's measuring rumen, that's the rumen degradable nitrogen part of the test. So that would be your ruminal release. The light blue bar would be, that would be total tract undigested nitrogen. So that's true bypass. It's bypassing the whole cow, actually. At least in vitro it is. So the difference is what's intestinally digestible, basically. So you can see these are rumen protected methionine products. In vitro, there's a product here that's 81% methionine bioavailability in vitro. There's one here that's 3%. That one has really high bypass all the way through the animal in vitro. Here's AminoSure XM, 56%. That's actually, those are the values we get in vivo, actually. So this actually works, this methodology seems to work pretty well for rumen protected methionine products. A lot of these values match up with what we've been able to measure in vivo with methionine products. Rumen protected lysine, you can see big differences here again, anywhere from 76% bioavailability here and here to, here's a product only 42% bioavailable. Here's AminoSure L, 76%. This is our new prototype, 72%. So those are the in vitro numbers there. This is some in vivo work. This is with the current AminoSure L product that we sell. This was in vivo work done in Dr. Mark Hannigan's lab at Virginia Tech. This was done a number of years ago. This was presented back in 2009. Basically, he measured in vivo 62% lysine bioavailability from that product. With methionine, there's some different techniques out there to measure bioavailability in vivo. We actually prefer this selenomethionine technique. This was developed by Dr. Bill Weiss and Norm St. Pierre at The Ohio State University. Dr. Reynolds mentioned Dr. Weiss earlier. They used to work together. We like this method. It's an in vivo method where we feed products to the cow. The way this technique works is you feed a consistent level of selenium yeast to the cow. So methionine typically contains sulfur, but if you feed a selenium yeast product, that methionine coming from the selenium yeast doesn't have sulfur, it has selenium in place of the sulfur. So you can use the selenium yeast basically as a tracer or marker in the milk protein that's produced by the cow. So then you can feed these rumen protected methionine products and calculate a bioavailability based off of how much of the methionine from this product shows up in the milk protein. We really like this technique as opposed to just measuring plasma methionine levels. This is some work with our AminoSure XM product versus a competitive product. Basically what this says is when they are fed at equal methionine levels, those two products have equal bioavailability. That's shown up in other published research, actually. When we doubled the amount of AminoSure XM fed, we had twice as much show up in the milk protein. So it's basically a second reading on the methionine bioavailability that matched up quite well.
So is this based on grams of methionine secreted by the mammary gland? Is that what it is?
Yeah. Yep. We've also utilized a lot of stable isotope methodology. Now, there's some different techniques out there with stable isotopes. So the problem with selenomethionine is that technique works great, but only works for methionine. stable isotope methodologies could be used for any nutrient that's out there. It can be used for all the amino acids. It can actually be used for choline. We've been doing some work with choline, looking at stable isotopes. So this was some work, again, this was done in Mark Hannigan's lab at Virginia Tech with stable isotope technique. And he measured a 55% bioavailability. The Ohio State work, I just showed you on the previous slide, that was a 54.25% bioavailability. So we get really good, actually very good repeatability between these different techniques. That in vitro technique, I believe that was like a 55% bioavailability. We got 55% here, selenium-methionine, we got 54.25. We model it at 54.25% bioavailability. And there you can see it right there. That's how AminoSure-XM is characterized in the models. It's 70% methionine, it's 54.25% methionine bioavailability. What ultimately matters to you as a nutritionist or producer is what's the metabolizable nutrient content? Because there's two things that impact that. I told you earlier that, of course, the nutrient payload can vary a lot between products. And so payload can vary and nutrient bioavailability can vary. So metabolizable nutrient content is just the payload times the bioavailability. So AminoSure-XM's 38% metabolizable methionine. That's what you're buying ultimately, is metabolizable nutrients. Okay, the last part I really wanted to talk about here, as far as the three legs of the stool of a good ruminant end cap, are feed and mixing stability. We've spent a lot of time looking at this. So we've done a lot of work with mineral mixing studies. So if you think about an encapsulated product, what's the harshest mixing environment you can put it through? We'll talk about pelleting later. Pelleting is very harsh, but as far as just mixing products, we test this actually in mineral mixes. If you think about a mineral mix, it's basically like taking sandpaper to an encapsulate. It's pretty harsh. So we've done a number of mixing studies internally looking at rumen-protected choline products, lysine products, methionine products, and even some of the slow-release urea products to see what effect mixing in a mineral mix will have on these products. These are the ingredients that we use: sodium bicarb, limestone, magnesium oxide, and a little bit of soy oil just to control dust in that mineral. And this is our recipe. So basically, depending on the product we're testing, we'll mix 45 kilo batches, and it's in a small scale mixer. I'll show you here in a minute. So we'll mix 41 to 44 kilos of the mineral mix with either 1 to 4.5 kilos of rumen protected product. And we mix those products for 3 minutes and test stability after that. So that's what this mixer looks like. It's a lab scale ribbon paddle mixer. And that's what it looks like loaded. That is not our product in there. I would actually be ashamed to have made that product right there. That's a competitive choline product. It's not very attractive. But that's what it looks like prior to mixing and then after we mix the product. So these are the results. So this is from some this is some work we've done with rumen protected choline products. So the solid line is that's what the product looks like unmixed. So if we just test the straight product, looking at ruminal stability over time, the dotted line is after it's mixed in the mineral. So this is Reassure here. Basically, it tests the same before and after mineral mixing. It's not being damaged by the mineral mix. This blue product here, this is a competitive choline product. You can see even the straight product without being mixed does not have very good ruminal stability to start with. It's at 8 hours, it's 85% loss. Mixing it with the mineral doesn't really make any difference. There's not much more damage you could do to the product when it doesn't have much stability to start with. This particular product, this is a competitive product. Before mixing, if we look at this 8-hour time point, it's about 30% rumen stable, but you can see the mineral mix really damaged it. It's only 10% rumen stable, lost 20 points of ruminal stability by mixing it with the mineral. So there are some products that are pretty heavily damaged by mixing them in a mineral.
Any impact of differential mixing, so paddle, ribbon versus tumble?
It's a great question that I don't know the answer to. Yes. Yes, it's a really good question. There probably is a little bit, but. So our general mixing recommendations, this would be true for any end cap, not just our products. So mineral mixing times, they should be equal to or less than 4 minutes to minimize excessive mixing and unnecessary abrasion to the particles. You should add the encapsulated products as late in the mixing process as possible just to reduce mixing time. What we found through the years, if you have at least 50% non-mineral ingredients in there, so 50% of any other carrier that's not mineral, that really reduces your potential for abrasion. Really softens that mix quite a bit. And you want to keep encapsulated products dry in sealed bags and below 50 degrees C. That's just true of any encapsulate. TMR stability. There's not been a lot of research done looking at this, but there was one published paper that's out there. There was a paper published back in 2016 looking at room-protected lysine products and how TMR stable they're done. It was done at the Minor Institute in the U.S. and it looked at basically at all the room-protected lysine products that were on the market in 2012. That work was done a number of years ago. It was published in 2016, and they found some pretty major differences in TMR stability. The slides I'm showing you now, this is some very recent research that we've done. This is going to be presented at the American Dairy Science Association meetings next month, actually. It's essentially the same technique that was published before, but with a slight modification to it. So basically what we're doing here, this is not even looking at ruminal stability at this point. This is simply taking these encapsulated products and placing them in a total mixed ration and letting them sit for up to 24 hours. And you're seeing how much, so they gently mixed, and you're measuring how much of that nutrient from the encapsulates lost to the TMR. So you're losing stability while it's sitting in the TMR, essentially. So these are rumen-protected lysine products here. So this is looking at lysine release over time. So we looked at 6 hours, so 0, 6 hours. So if you were feeding 4 times a day, 6 hours, sitting in the TMR. Fed twice a day, 12 hours. Fed once a day, 24 hours. So how do these products look over time just sitting in a TMR? And this is looking at release. So you can see these two products they're not TMR stable. They have very high levels of release just being lost to the TMR. That lysine is being lost into the TMR. So those products, even at 6 hours, have 75% loss to the TMR before the cow even eats it. Some of these products are very stable. This is actually our new lysine prototype here. It's very stable out through 24 hours in the TMR. So some pretty big differences here, but particularly with those products, that what I'll tell you is that mimics that paper that was published in 2016.
Ask you a quick question.
Yeah.
So you mix this with a TMR. What is being measured to tell that it's being released?
You're measuring free lysine in the TMR then. So you basically what you're doing.
You're putting that in a solution?
Yes.
Okay.
Yes. You dunk it in distilled water for like 2 minutes. Yeah. So you're solubilizing the lysine and measuring it. Yep. Great question.
Excuse me.
Yes.
In the case, then how do you delineate the lysine from the TMR base and the lysine from the protected lysine? Because you are measuring the amount of lysine that is released into the medium or something like that.
Yep. So you run a negative control to start with. So the treatments are you're running a control with no added lysine to it. So you're measuring your basal lysine. And actually, we also have a treatment where we add straight lysine HCl to see how much of that's released, and then we have treatments with the different products. This is the same technique, but this is with rumen protected choline products. There's never been any research published looking at rumen protected choline stability in TMRs, but it's kind of the same thing here. Same technique, just looking at choline chloride. And rumen protected choline in this case. So again, some of these products are not stable in the TMR. At 6 hours, a couple of these, again, they're 70 to 75% released to the TMR. At 12 hours, they're over 80% released. At 24 hours, they're completely released to the TMR. So they would have no ruminal stability, basically, at that point. There's the Reassure XC product, and this is our Reassure Classic here. So big differences in TMR stability. Pellet stability. I know this is a very popular topic some places. We've done a lot of work looking at this through the years. It would be great if encapsulates were pellet stable. I don't believe they are. We've sort of changed our thinking on this through the years, but we've done a lot of work in recent years looking at different products that are out there. So these are rumen protected choline products. We've looked at methionine products, measuring stability in a pellet. With these different choline products, basically, they're not very stable in a pellet. You're going to lose a lot of efficacy when you pellet it. I mean, just think about what's happening when you pellet a product. High temperature. So all these products, even if they're polymer products, every encapsulated product is lipid technology at the base of it, right? So even if you're forming polymers, it's mainly lipid encapsulation that's happening there. So you're going to melt these products. You're going to lose efficacy. There's a lot of friction, a lot of pressure, and we've utilized different techniques to look at this, and there is not much left that we would consider to be well encapsulated after going through a pellet mill. So these are our current pelleting recommendations. This would be true for any encapsulated product. I don't recommend pelleting them. You're going to lose efficacy. I would say our products are just as pellet stable as any other that are out there. They're not stable in pellets. They're all the same. They're not stable. So I don't recommend pelleting. If you want maximum efficacy of a product, I would recommend not pelleting it. I'm not saying it absolutely won't work, but you're going to have to feed more of it to get the same efficacy. They're expensive products, so do whatever you can to preserve efficacy of the product. And it's our desire that producers get the maximum benefit from our products. We've spent a lot of time, a lot of research dollars developing products, and we want them to perform on farm. Then ultimately, what matters in the end is biological response. We go through all those other steps, but product's got to work in the cow. The cows don't lie, right? So this is research. This is with AminoSure-L. So this was presented back in 2009. Just looking essentially at a lysine deficient diet. So an unsupplemented diet versus 30 grams of AminoSure-L per cow per day or 60 grams per cow per day. And when we supplemented either level of AminoSure-L, we got a bump in dry matter intake. We got an increase in milk yield, about 2.5 kilos of milk yield. Didn't really matter whether it was a 30 gram or 60 gram dose. So we're meeting, in this case, we're meeting those cows' lysine requirements at the 30 gram dose. We didn't really get any added benefit to feeding the higher dose.
Lysine in AminoSure-L.
It's just short of 25% metabolizable lysine. It's 24.6% metabolizable lysine.
8 grams of metabolized lysine.
Yeah. Yep. Rumen protected methionine. Methionine studies, to me, they're easy to run. It's very easy to have a methionine deficient diet from a milk protein perspective. So this is an AminoSure-XM study versus a competitive product. So control, competitive product, AminoSure-XM. These two products were fed at equal metabolizable methionine levels, and we saw the expected response. We got a bump in milk protein. These are true milk proteins. So these may look low to you if you're used to seeing crude protein in milk. They're about 0.2 lower than a crude. But we saw the typical response here. We saw an increase in milk protein percent and numerically an increase in milk protein yield, but that wasn't statistically significant. But 50 gram bumps in milk protein are actually pretty good on the farm. ReaShure, you've seen a lot of this research already. We have 41 peer-reviewed publications now on ReaShure and ReaShure-XC. Dr. Santos showed this is the full lactation effect that he showed from the University of Florida research. That's the second study he showed out through 15 weeks of lactation. This is the more recent research. This is with ReaShure-XC. This was done in Barry Bradford's lab at Michigan State University. First 16 days in milk. That was a 3.6 kilo per day increase in milk yield. Very nice response there. That followed out through 12 weeks in milk, 3.5 kilo milk response. So again, the ReaShure-XC is only fed 21 days prepartum or 21 days postpartum. These are carryover effects that we're seeing in these studies.
On Barry Bradford's results,
Yes.
how many grams did you feed?
So it was 12.9 grams of choline chloride, just like our ReaShure studies. It was just it was the ReaShure-XC, so a more concentrated product. There actually were two treatments there. There was a 12.9 gram dose of choline chloride, and there was about a 1.5x dose there as well. We didn't actually see a dose difference in that study.
Did you feed? How many ions were in that 12.9, or is that ions of choline?
That's grams of choline ion. Yeah. 30 grams of ReaShure-XC. We fed you 30 grams or 45 grams of ReaShure-XC. Yep. Yep. This was another study. Anna showed this, but this is basically looking at two of the newer studies. So this was work done at University of Wisconsin that was published last year. This was the work from Michigan State published last year. This is the graph. I think you showed this, Jose. This is the meta-analysis graph. This is energy-corrected milk yield. So that Wisconsin study, they were kind of off the chart. They were, those cows were at 55 kilos of energy-corrected milk. We still saw positive response here, a 2 kilo energy-corrected milk response. The Michigan State work, this is milk yield here in this case, and we saw 3.5 kilo milk response there. Even at those high levels of production, we're still getting those benefits. So in summary, there are a lot of differences in encapsulated products for dairy cows. What are the differences? Design of product varies. Coating types, amount, and composition can vary considerably. Manufacturing differences, we talked about the matrix versus the true end caps. There are other variations within that. Nutrient content, or what I call the payload, can vary substantially. Bioavailability can vary substantially. And feed stability is a huge thing that we don't look at very often, but there are big differences in feed stability between these products. If an end cap's not feed stable, you truly are losing right out of the gate. Before the cow even eats it, you're losing a lot of efficacy of the product. For rumen applications, true encapsulates are the preferred application here. And there's 4 important features of a good ruminant end cap: good ruminal stability, good nutrient bioavailability, feed and TMR stability, and ultimately biological performance in the cows. So with that, we will have lunch. So Tanya, you're going to give us directions here?